Hello and welcome to my students. Today's lectures we are going to discuss the topic superconductivity. In these topics, the last lectures we have seen what is the superconductivity and what is the critical temperatures or transition temperatures. Now we have seen the Messner effect. The scientist in 1933 by Austrian radio engineer Walther Messner, together with R or same field, they will be found. They was found if a superconductor was placed in a magnetic field and then cooled below its critical temperature, it expelled all the magnetic flux. This complete exclusion of applied magnetic field came to known as the Messner effect. And this effect, which is indicated by using this diagram, if the superconductivity involved just vanishing of electrical resistance, and they could have be explained here. For example, this is a normal conductors, and these normal conductors we can place at helium they will be cooled below, this is critical temperatures. Then what happens? This normal conductor behaves superconductors. Then by applying this applied magnetic field by these superconductors, then what happens? These magnetic flux lines, they will expel by the superconductors. Similarly, other case, we shows that these normal conductors directly applied the applied magnetic field for those normal conductors. Then we observe that these such magnetic flux lines, they will penetrate or they will pass into the normal conductors if this temperature is greater than the critical temperatures. Then these normal conductors, when cooled below critical temperatures, then what happens? These magnetic flux lines, they will expel by these superconductors, which times the temperatures of that normal conductors is below critical temperatures. Now we have seen discuss in details what type of the mechanism which is operate in first step. In first case, firstly the conductors we place in cooling to a temperature below its critical temperatures, and therefore it makes superconductors. And then these superconductors we can place in uniform magnetic field, and these magnetic field lines force will not able to penetrate by the superconductors. According to Faraday's law of induction, the current induced in superconductors and will oppose or expels magnetic field can be happens. In second case, what happens? Firstly, these normal conductors we can place directly in uniform magnetic field. Then what happens? The magnetic lines force, they will penetrate through it. Means these magnetic lines pass through these normal conductors. But then these conductors, when cooled below its critical temperatures, hence the magnetic flux lines which is inside in conductors, they will completely expel from superconductors. Means they will go away from superconductors. And these phenomena are contrary Faraday law of induction. Superconductor is not perfect conductors, but also it is a perfect diamagnetism. And this remarkable discovery, the law of induction, the superconductors, which is the perfect conductors as well as perfect diamagnetism. The next points we have going to the conventional superconductors. In these conventional superconductors, we have see how will you convert the normal conductor to superconductors. These diagrams, which are the red colored, these lattice points are shows the lattice of tin, and these green colored green colored these metals which shows niobium. Conventional superconductors means the superconductors required liquid helium for cooling, and therefore they are called as conventional superconductors. What do you mean by conventional superconductor? Means the superconductor, they will require the liquid helium, which is called as a conventional superconductors. For example, the niobium metals has highest critical temperatures as about 9.50 Kelvin. The large number of compounds and alloys of the niobium behaves the material which has high critical temperatures. For example, those tables which are clearly shows that which types of the components or the alloys of the niobium shows their critical temperatures. Firstly, the niobium tin, the last slides like these slides of this niobium tin, they will have the superconductors having the critical temperature is about 18.3 Kelvin. Next superconductors of niobium is niobium germanium. It having a critical temperature 23.3 Kelvin. Similarly, niobium aluminium, it having a 17.5 Kelvins. And niobium nitride is having the 16.0 Kelvin. So this is the value of the critical temperature for this niobium alloys. Niobium alloys which are brittle and therefore it cannot be fabricated in the form of wires. Hence, they have been manufactured in sufficient quantities to use as to make the coil. Hence, this vanadium gallium, which is found to 16.5 Kelvin, niobium germanium 23.3 Kelvin, which has highest critical temperatures. Similarly, the alloys like the niobium tin, vanadium gallium, niobium aluminium, niobium germanium, it has the A3B type of these superconductors, where capital A is the transition metals like the niobium, vanadium or tellurium and zirconium from 13th and 14th group element. These compounds which are known as A15th group of elements or A15 group of compounds. Capital B1 is the another type of conventional superconductors like the niobium nitride has the critical temperatures which is found to be 16 Kelvin. The structures has many vacancies and therefore they filled with carbon, which results the compounds having the critical temperatures of about 18 kelvins.